Hello, welcome back to our chemistry course. Today we will begin with a very complex subject, which is the atomic theory. And we've subdivided that into 4 sections because it's so vast. We cover so much territory. So please forgive me if we can't be completely into every alley of this subject matter. So today, atomic theory 1 deals a little bit with the historical events that led to this concept of the atom. So let's see what we have here today. Topics, early concepts. Now, who can trace really the earliest concepts, because there weren't always people taking notes. Lots of information is lost. So now we sort of believe that the ancient Greeks developed the atomic theory initially. And then lots of time elapsed. The atomic theory was still considered here and there, but not in a very concrete scientific way. Dalton really was the one who got it back into focus, and he also used the atomic weights, an early set of atomic weights that described the individual atoms as well. So that is really the beginning of our modern chemical atomic theory. Then, as an offshoot of this discussion, the proportion laws were developed, such as the law of definite and multiple proportions. That is very important for chemistry as far as compounds go. And then, of course, the nature of the electric charge. That matter is electrical was also revolutionizing the scientific development in this field. And the discovery of ions, and Faraday, Arrhenius, and Stoney played a role in this concept of ions or charged atoms. So let's move on and see how this whole story began. Early atomic theory, we have Democritus as being the prime philosopher that considered the ultimate chemical unit of matter, which is the atom, coming from the Greek name atomos, meaning indivisible. People always argue, okay, that we know now that the atom is more divisible than that, but for the chemistry part of our discussion, the atom is practically the ultimate particle. And, of course, the electrons that are part of the atom. So the nucleus is important, but not so important for chemical transactions per se. So the Greeks had a lot of time on their hands because they had a beautiful country, beautiful beaches, sunshine, and they could philosophize and discuss the nature of matter. So Democritus was one of the important Greeks here in this category, and there of course were others that is interesting from the historical point of view. But remember, we have to discuss so many concepts from the beginnings to all the way to the quantum mechanical model of the atom. So we have a ways to go. So let's move the time arrow and go ahead to Dalton. Dalton is such an important person in chemistry because he was involved in many things. Dalton was an English schoolmaster, a teacher, in other words, and also Quaker. Very self-disciplined. He was interested in many fields. He discussed the atom, as we already have fathomed by now. And then also he delved a lot into the gas laws. There's a Dalton gas law, for instance. So he was the one who developed the symbols, many of the symbols, as well as the atomic theory that is pretty valid for our chemical discussions. That means that all elements are endowed with a certain type of atom that makes up their substance, and each atom having a certain amount of mass or weight. Remember, weight is not really mass. It is mass times the Earth acceleration. So it is actually a force, but sometimes we interchange these two terms without knowing the exact difference or not considering it. So Dalton already worked out atomic weight table. For instance, here we have some, like hydrogen is 1, so he based everything on multiples of hydrogen in a sense, with fractions. Nitrogen is 4.2, the mass of hydrogen, carbon 4.3 times, oxygen 5.2 times, sulfur 14.4 times, and so on and so on. Now let's look at Dalton's actual 4 stipulations, or postulates, we could rather say, of the atomic theory that he conceived. So matter is made up of indivisible atoms that stay unchanged during a chemical change. So they're different sizes and different masses. And he also postulated here in number 2 that each element is made up of one type of atom, which has its characteristic properties of size and mass. And a compound is nothing else but a distinct mix of these elements in certain proportions. So here we see water. We have oxygen bonded with 2 hydrogen atoms, so that makes this compound. So a compound has 2 or more elements involved, and each element having its own type of atoms, and therefore each compound also has its particular ratio of elements involved or atoms involved to make a certain distinct composition. A chemical reaction, in other words, then, means that the atoms just rearrange themselves in different combinations. So for instance, oxygen, move that up a little bit. Oxygen, diatomic molecule, and hydrogen, they just break their old bonds and make new combinations, and thus a new compound is born. So, old combinations make new combinations. So in a way, we're just shuffling the atoms, breaking old bonds and making new bonds to create a chemical change. So it's very, very straightforward. And this idea, or these ideas, paved the way to our modern chemistry. Here we have Dalton and also Faraday. Faraday is another very important early scientist who didn't really have a formal education, who was a bookbinder, but he was involved with reading many of the books that he received for binding. He was self-taught, and then by some stroke of luck, he got a free ticket to one of the famous lectures of Davy, and he just got interested in chemistry, and then later became even his assistant, and even got a professorship later on in the college where he worked later on. So one of the most famous scientists without any formal education. So it's not always important to receive an education. You can be self-taught, and if you are motivated and interested, anything is possible. So he learned, or also observed, that compounds can be separated with the help of electricity into their constituent elements. So we have here a compound like hydrogen chloride or hydrochloric acid, and electrons will separate that compound into hydrogen and chlorine. And with the help of a proper setup, like an electrolysis apparatus, we can visualize or follow this type of change that is a result of electronic interaction with matter leading to a chemical change. Meaning actually the bonds are broken and we have, as a result, the constituent elements. So it's the reversal of a synthetic reaction, a decomposition reaction. So something is going on, so the electrons must play a role in this change. Here we have a setup of an electrolytic cell, as we say, with two electrodes, the cathode and the anode. The cathode attracting the cations, which are positively charged. Cathode, therefore, must be negative. That means it's the electron donor electrode. And the anode is positively charged and absorbs electrons so that the circuit through the liquid here is closed. So in the end, we have hydrogen gas developing on one side of this chamber and chlorine gas actually developing on the other side. We call this reaction today a redox reaction because we have an exchange of electrons. You see, when you look at hydrogen, it picks up an electron. First of all, of course, we must consider that HCl decomposes into protons, which are hydrogen ions, and chloride ions. Now, the proton or the hydrogen ion receives an electron from the cathode and is neutralized to a neutral hydrogen atom. Now, this doesn't last long because two hydrogen atoms will want to combine to make a diatomic molecule to get their stable electron configuration, and then the gas is trying to get out of the liquid into the environment. So it bubbles out. We have gas evolution on that side. And on the other hand, the chloride ion gives up an electron. That means the anode picks up the electron, and we have a neutral chlorine atom. And the chlorine atom doesn't like to stay by itself either. It wants to make an octet, so they share electrons with another chlorine atom, and then we have a diatomic molecule. And that is chlorine gas for you. So we go from an oxidation state of +1 to neutral, that means reduction, or going from a higher oxidation state to a lower means reduction, and the reverse is going from a lower to a higher oxidation state, which is called oxidation. So we call this reaction in total redox, the red ox. Isn't that easy to remember that way? Now, what is also interesting that Faraday coined a lot of these terms which are so important today with an assistant or associate named William Whewell. So they invented the names electrolysis, the electrolyte, the anode, the cathode, the anion, the cation. So everybody knows that these terms are so important in chemistry, in physics, etc. So the electrical nature of matter was so important in determining also the so-called composition laws or proportion laws. And we see here in this view graph or in this slide how the electrolysis of water also produce hydrogen and oxygen gas by decomposition reaction. Only we have here a certain device that separates the two gases from one another. We don't want these gases to come in contact with each other because they would make an explosive recombination to form water. And that would be dangerous in the lab setting. So therefore, the gases are separated, like separating a dog from a cat, so to speak. Not that it's always so bad. So we have a method of isolating these gases separately. Now we have water which always produces the same volume ratios of the constituent elements, oxygen and hydrogen. But per mass, we also have a consistent ratio of the elements. And that's what we call the law of definite proportions, which was actually developed by Proust as French chemist. So you see, water always has the same mass ratio of oxygen to hydrogen. And that's a characteristic of water, because if it would not be, then we would have completely another compound. For instance, hydrogen peroxide does not have the same ratio of the elements as far as their masses go. So it has an extra oxygen, so it must be much heavier. So it has a higher percentage oxygen than water has. So let's look here at the water molecules. The mass ratio is about 11% hydrogen and 89% oxygen. So it's roughly, you could say, almost 1 to 9. From this law, we can derive the law of multiple proportions. Now, it's different from the definite or consistent proportions. Here we only talk about one compound. But when we talk about multiple proportions, we compare many compounds of the same elements. Now, some elements can make a big variety of different combinations, but oxygen and hydrogen can only make two. And one is water, and one is, you well know, hydrogen peroxide that makes your hair blonde, but also, of course, disinfects cuts and bruises, or if you were going into a disease-infested area, hydrogen peroxide would help you survive there. So let's look at water and hydrogen peroxide. Here the ratio is about 2 to 16, or 1 to 8, and here the ratio is 1 to 16. So you see the percentage of oxygen is much higher. The same we can do for the two compounds carbon monoxide and carbon dioxide. They also happen to have only two possible products. The carbon monoxide, combination 1 to 1, atomically speaking, but mass-wise it's about 3 to 4. And carbon dioxide is about 3 to 8 ratio in mass. So we have two oxygen atoms, and if we leave one element constant, for instance the carbon, then the law of multiple proportions states that the second element, the ratio of the second elements compared to each other, or the amount of the second element compared, only the second element compared, these ratios will also be whole number values. Whole number ratios. See here with carbon monoxide we have 3 to 4 and carbon dioxide 3 to 8. So the ratio would be 4 to 8, and that we can break down to a smaller ratio, and the end result is 1 to 2. And also we have the same situation here with water and hydrogen peroxide. So if I leave hydrogen constant and only compare the second element, then they also behave in whole number ratios. And that you can combine into the law of definite and multiple proportions. So this indirectly is a proof for the existence of atoms. So these are the composition laws. I already mentioned that Proust, a French chemist, was involved in starting to define the law of definite or constant proportions, which we also call the law of definite proportions at times, by itself without the constant ratio involved. It was recognized by Proust in 1797 and stated officially in 1799 and 1806 as follows: we must recognize an invisible hand which holds the balance in the formation of compounds. A compound is a substance to which nature assigns fixed ratios. It is, in short, a being which nature never creates other than balance in hand, pondere et mensura, which is a Latin phrase. So here again we have the same workout. Here I used AMU as mass ratios, but you can use grams per mole, you can use grams. So as long as you use the same units, the ratios should always be constant. Here we see it enlarged. Now, are atoms for real? This is an interesting picture that we see here. Those are what we call scanning, tunneling microscopic images, which work sort of like a needle testing the surface of an atomic array, similar to a needle testing a record in the old record players. Not quite the same, but it's sort of a little hint that it might be a similar concept. So we see, in a way, the individual atoms here on the surface. For instance, in the bottom picture, we see the nice little hexagons that the carbons make in the graphite allotropic form of carbon, the graphite lattice. And graphite is a conducting material. So the important thing is here that you need conductors in order to get these images. And then on the left top, we have the gallium arsenide, and you see two atoms are involved. It's very interesting because people can also observe changes in the surface of structures and test catalytic properties and so on and so on. So it's really quite interesting. And how does this principle work? Well, it's fairly new. So these people received the Nobel Prize in 1986. Those were two Swiss individuals that worked for IBM Zurich. And here we see the principle. This is a graphite lattice. This is the picture that we just saw in real life. This is my little drawing here that shows you that we have three coordinates in space, so it's a 3D image. It sort of reminded me of egg cartons or these foam rubber mattresses that you can buy. And this is, in short, how it works. We have here our atomic array, the surface. This is a tiny little probe. It's usually tungsten and very, very thin, almost a monoatomic layer, you could say, attached to a piezoelectric XYZ scanner that gives the 3D image. And so it sort of probes up and down here on the surface. It's connected to an electrical current. And then it sort of scans the surface, and the tunneling is actually penetrating the empty spaces of the quantum arrays of atoms. So it's an atomic landscape that you're probing, and it really brings us a variety of very interesting pictures. Now, as I said, the limitations of this technique are that the materials, as well as the probe, have to be conductors. And that is not always the case. So we have to limit this to only certain materials. But it certainly gives us some concept that there are something like atoms. But we can't see them individually, but in a nice little landscape. And here we see it enlarged. And here in the end, we see a lone chromium ion on a silica surface. And this is an STM image, again, a scanning, tunneling, microscopic image. So this technique is called scanning, tunneling, microscopy. The electron microscope also has a good resolution. The resolution is about 0.2 nanometers because electron beams are used. And you also can see some atomic arrays, so it's also in many ways quite good. It was developed by Crew in Chicago in 1970, the electron microscope photography of uranyl acetate on an ultra-thin carbon layer. I don't have the original picture, but this is sort of the pattern. So many beautiful things are revealed now that are, of course, very exciting for an artistic, from the artistic point of view. So if you're a scientist and an artist, then you have two worlds here together. And here we have another image of a silicon surface. And with this, I'd like to conclude our introduction to atomic theory part 1. And we will go soon to the most important experiments that led to the modern atomic theory. And that happened pretty fast. When you think old Democritus on the beach of Greece, then many, many, many years until we came to Dalton, so almost almost 2,000 years, maybe 1,500 years. Don't quote me, please. And then it was almost like an instant development of the earlier modern theory to the most recent modern theory, the quantum mechanical model of the atom. And now, as you know, lots of research is done in the nuclear realm of the atom, all those particles that the physicists deal with, the particle zoo. So you see, there's a lot going on in this field. And we will talk next time about the cathode ray tube, how it developed the ability or the concept for us to study particles in action, to test their properties. Are they neutral? Are they deflected by electrical or magnetic fields? Modified cathode ray tubes, and then the establishment of the three fundamental particles, the electron, the proton, the neutron. And they were discovered in this sequence. Remember, the atom, as we understand today, has the electrons on the surface. So the surface can easily be scraped off. So when I wash my hair and comb through my hair, I get these little sparks. So that is an electron emission by a mechanical means. So we can have very many ways of getting the electrons scraped off from the atoms. And cat's fur is very useful for this purpose, to get stray electrons. And electrons are always easily removed, but they like to go back to their atoms. And when they go back to their atoms, you will know that light can be given off. So like the sparks when you comb through your hair. So I'd like to thank you for listening and your attention. And we'll see you next time when we go on talking about this exciting field. Thank you very much.